Hello, dear students. Welcome back to the session. Now, in this session, we will discuss design procedure of a simple band break. So, as we have already come across, what is band break? A band break is nothing but a type of break in which a band or a flexible band like belt is used, which is wrapped on a drum. Partially, it is wrapped on a drum so that one of the ends of that band is connected to the end of the lever that is at the fulcrum point, and the other end of that band is connected to the lever. And as there is a if the force is applied at the end of the lever, so that what happens, the tensions in the band that will be increased, and tangential force that results in the generation of a brake or say torque, or the frictional force that is exerted in between the brake and the band, and then the brake drum is going to retard its motion as well as it is going to stop. Now, with respect to the since concept or design concept of simple band brake, there are some few steps that we have to follow here. So initially, to calculate the actuating force, what we have discussed in the previous session by taking moment about fulcrum point. So to calculate that F, we require the value of tangential force. So tangential force is calculated with the known value of torque. So in these steps, there are say there is a first step, that is torque to be transmitted or torque required to overcome the friction exerted between the band and the brake. So the torque is calculated by using the fundamental power equation with the known power value in kilowatt is to be substituted in the LHS here. So in the RHS, the value of a torque T is the only the unknown parameter. So this torque T is to be calculated. So the value of torque T, what we get in Newton meter first, and then the torque which is in Newton meter, that is to be converted into Newton mm by multiplying the value by 1000, that is 10 raised to 3 Newton mm. So this torque is required in the next step. So next step is to calculate the tangential force, so which is denoted by the notation Ft here. So that Ft is calculated with the known equation of torque. So torque T is given by Ft into R. So with the help of this torque Ft, that is the tangential force exerted on the drum, is calculated as the ratio of torque to the radius of the drum, where R is radius of the drum. So the value that you get in newtons. So this value is in mm, radius of the drum value. And once you get these values, the next step is to get the values of uh, tensions in the tight side and slack side of the band, that is F1 and F2, irrespective of the direction of rotation. So to calculate the tensions in the band, so the equations what we have to follow, which are there in the data handbook, as already we have discussed the conversion of F1 and F2 in terms of Ft and e raised to mu theta. So this is by using the fundamental expression itself, that is F1 minus F2 equal to Ft. So by using this fundamental expression itself, and also we know that another relation, that is F1 by F2 is equals to e raised to mu theta. So by using this relation, one of the term is to be eliminated, another term is transformed into other form, so that you will be getting the equation of F1 and F2, tangential force or the force on in the tight at the tight side and slack side of the band. So this equation is available in the data handbook, page number 269. So by using this equation, you have to substitute the values of Ft, which is calculated in the previous step. Mu is coefficient of friction, which is given, that is to be substituted here, and theta value, that is in radians. So theta value is the angle of lap or angle of contact, so which is to be substituted in terms of radians. So that value is to be substituted in radians. So if it is given in terms of degrees, so convert that value in by multiplying pi by 180. So substitute here, so that you will be getting the values of F1 and F2. So this is the theta angle of lap in radians, and mu is coefficient of friction. So by referring the equation, that is page number 269 of data handbook, you can calculate F1 and F2. So once you get F1 and F2, The next step is to go for the calculation of operating force. So to calculate operating force F, so there are two conditions. Either the drum is rotating in clockwise or it may rotate in anti-clockwise direction. So here the drum is rotating in clockwise direction, and the one of the end of the band is connected to the fulcrum point and the other end is connected to the lever, and the distances they are represented here B and A respectively. A is for the distance of F from the fulcrum point and B is the distance of the end of the band from the fulcrum. So if since it is rotating in clockwise direction, so this resembles figure E of data handbook page number 270. So by seeing this figure, so here we have to take moment about point O, so that I will be getting an equation that is F into A. So this is this particular term, and there is a moment given by F2. So F2 into B, it is F2 into B. So this is another term, but both are having the opposite direction, so hence it is minus. And finally you will be getting the equation of F as F2 into B divided by A, and which is given by equation number 13.19C, page number 270 of the data handbook. So this thing that we have to refer from directly note down the equation from the data handbook or by using the fundamental expression of moments equilibrium condition. So you can use the equation of F here, or you can get the value of F. So this is one of the case. So for clockwise rotation, similarly for anti-clockwise rotation, suppose if the drum is rotating in the clockwise direction, suppose if the drum is rotating in the clockwise direction, counterclockwise direction, so that is CCW, counterclockwise direction or anti-clockwise rotation. So in that case the F1 is shifted, so this is the tight side because this is the pulling side now, and this one is the slack side, so slack side tension is F2, so that the equation becomes F1A minus F1 FA minus F1B. So this is what the equation what we are getting here. So F is equal to F1B divided by A. So this is equation number 13.19D, page number 270. So once you get the value of F for clockwise and F for counterclockwise. So you will be getting two values, F for clockwise value as well as F for counterclockwise direction. So in both the cases, the value of F is neither equal to 0 nor less than 0. So that is what the condition here. That's why this simple band break is not self locking break. It is, see, out of these two F values, so the maximum value is to be selected. The maximum value is what? The maximum of either for this or for this. So F max is to be selected. So either or this value, say either F for clockwise or F for counterclockwise, whichever may be the maximum. So that is to be treated as F max. So this value that we have to use in the rest of the equations. So this, after this we have to go for the design of band. So band is having a thickness or rectangular cross section which is wrapped on the around the drum. So H value is usually given. Suppose if it is not given, then we can use H is equal to 0.005 times D, where D is what? That is the diameter of the drum. So you can use equation number 13.18 N, page number 269 of the data handbook. So this equation again we are using in the differential band break also. So there also we have to remember this equation, and then we have to calculate the width of the band. So width of the band is given by B. So B is equals to F1 divided by H into sigma D. So this is equation number 13.18 O, 13.18 O, page available in the data handbook, page number 269. So by using this equation, say B is to be calculated here. F1 is the tight set tension which is known, which is calculated in the previous step. H is the thickness of the band which is given or that is to be substituted after calculating this one. And sigma D is the design stress of the band. So usually this value that varies from 50 Newton per mm square to 56 Newton per mm square. So this up to this particular range that we can select it, 56 or 55. So this is the standard value for the sigma D. If it is given, that is well and good. If it is not given, you have to use 50 or 55. So that you have to remember. So this is the thing that we have to consider here. So after getting the value of width, that is b, so these are the two parameters related to the band dimensions. These are the two parameters related to the band dimensions, thickness as well as width. Suppose sigma d, if it is not given, you have to use the value as 55 Newton per mm square. And next step, that is related to the design of lever. Design of lever. So with respect to design of lever, so here we have to consider the given beam or the given lever as the cantilever. Given lever as the cantilever, because it is fixed at one end and loaded at other end, that is F. So this is to be considered as the what cantilever, and here we have to consider either F1 or F2. So to calculate maximum bending moment, we have to use the equation F max into A. So F max is nothing but what? F max is the maximum value of F, maximum value of F for counterclockwise and clockwise rotation. So this distance is A here. So here F max is maximum of F, maximum F of clockwise or counterclockwise rotation. Clockwise or counterclockwise rotation. So this is the value of F. F you are calculating for clockwise rotation and as well as counterclockwise rotation. For which rotation the value of F is maximum, that value is to be treated as maximum F, and that is to be used to calculate the maximum bending moment. So since it is considered or treated as a beam here, so we have to make use of the bending equation. M by I is equal to sigma by C, or sigma is equal to M by I into C. So here this is the value of B1 and this is the value of H1. So usually H1 is greater than B1. H1 is greater than B1. So that will be given. If it is not given, you have to assume that value as twice or thrice the value of B1. So here it is assumed as rectangular cross section which is known. So I is equal to B1 H1 cube divided by 12. So B1 is the width and H1 be the depth or thickness. Depth or thickness, and this is width here. So with respect to that, I equal to moment of inertia. Moment of inertia is given by B1 H1 cube divided by 12, and C is the CG distance from the extreme fiber, which is given by H1 by 2, half of the thickness, and sigma be the stress used for the stress of the material, or the material which is you are used for the lever. For that material, you have to write the value of stress. Usually if the material is not given, suppose in that case we have to assume C40 or C30 steel. So for that, you have to note down the value of sigma y from appendix, and also we have to assume suitable factor of safety, so that we can get the value of sigma as sigma y divided by FOS. Sigma y divided by FOS. By using this relation, you can get the value of sigma here. And anyway, you know the value of M, that is F max into A, and H1 by 2 is the C value, and B and H1 cube divided by 12. So that it is simplified and you can get the value of unknown parameter, either b1 or h1. So either of these two value or the relation between them, that will be given. So h1 is usually twice the b1 or thrice the b1 value. So this is the thing that is related to the design of simple band break. So with this these steps, we have to solve the problems on simple band break. Now let us consider a simple band break. Example of simple band break, or one simple problem. Say simple band break operates on a drum of 600 diameter. So the diameter of the band is given, drum is given as 600 and this is running at 200 rpm. The value of n is 200 rpm and r is 300, that is the radius. And this is absorbing a power of 15 kilowatt, and cof is 0.25, that is mu, coefficient of friction. And the brake band has a contact, or that is angle of contact, of 270 degrees. That value is 270 degrees. So it is to be converted into radians. It is to be multiplied by pi by 180, which is the conversion factor, so that the value of theta is 4.71 radians. And in addition to that, there are some more information is given. See here, one of the end is fastened or to a fixed pin. That is what fulcrum point. So the end of the one of the end of the band is fixed, and the other end to the brake arm at 125 mm. So here one end of the band, one end of the band that is fixed here, that is fixed here, and the other end is connected to the lever with a distance of b. What is that b value is 125 mm as it is given in the statement. And the arm, straight arm, that is having a length of 750 mm. So from this point to this point the length of the arm is 750 mm, that is nothing but a. And the things are given like this, and determine what to determine here: maximum effort required to stop the rotation of the drum. So that is the maximum value of f. So f for c clockwise as well as counterclockwise, that we have to find out, and maximum among these two is to be considered as the f max, or the maximum effort required. And width of 2.5 mm, that is h value is given, and sigma d, which is given here as 56 MPa, and design the lever. So these are the steps or the things that we have to calculate here. So once the things are noted, the next step, so as per the design procedure, so calculate the torque value first. So according to that equation, say P equal to 2 pi nt by 16 to 1000. So here you will be getting torque in Newton meter. Once you get torque in Newton meter, convert that one into Newton mm by multiplying the value by 1000. Next step is to calculate the tangential force Ft. So Ft is given by T by R. T is known and R is radius of the drum, that is 300. So that Ft is equal to 2387.5 newtons. So once you get this value, the next step is to go for the calculation of F1 and F2. So here we have to refer the data handbook, page number 269, what we have earlier considered. So 269, by using this page, there are equations for F1 and F2 in terms of Ft as well as e raised to mu theta. So e raised to mu theta is nothing but e raised to mu is 0.25 multiplied by theta 4.71 radians. So that value is equal to 3.25. So e raised to mu theta, and that value is to be substituted here. So that F1 value is 3449 newtons, and F2 what we get 1061 newtons. So once you get these two values, the next step is to go for the calculation of operating force for clockwise rotation and for anti-clockwise rotation. For clockwise rotation, again we have to refer the data handbook figure E and page number 270. So according to the given statement, one of the end is fixed at fulcrum and the other end is at a distance of B, that is 125 mm, and A is, that is the total length of the arm is 750 mm, and the drum is rotating in clockwise direction as it is given, and the angle of contact is 270 degrees. So by using the equation of equilibrium, that is Fa, bending moment given by M, F and F2, that is what Fa equal to F2b, so that F value that we can get here. Directly we can substitute the value of F2, which is calculated in the previous step. And then for using the same condition, that is for counterclockwise rotation. For counterclockwise rotation, the pulling side, that is F1 is shifted towards right side and F2 becomes toward the left side, so that the equation of F equal to F1b divided by A, by referring the same equation or the same data handbook, page number 270. And F value that you get here is 570.84 newtons. So with respect, by comparing both the values of F for clockwise and for counterclockwise, so this is the value for clockwise rotation, and this value is for counterclockwise rotation. Counterclockwise rotation. So by comparing these two values, this value is greater. So you have to consider this value as the maximum force. So which is required at the end of the lever to apply the brake. So after this, the next step is design of band. Since band thickness is given here, but even though if I calculate that value is 3 mm, and it is to be considered here as 2.5 mm as it is given. So width of band is given by F1 divided by H1, H into sigma D. So F1 value is 3449 and H value is 2.5 given. Sigma D is also given as 56. If suppose if it is not given, assume that value as 56 only. And so that the value of width is 25 mm. Next thing that is required here is the sixth step is to carry out the design of lever. So to carry out the design of lever, since the material used for the lever is not given, so assume the material used for the lever as the C40 steel, as it is a C40 steel. So we have to refer the data handbook appendix 1, appendix 1, page number 464. So there the value of sigma y is 324 and factor of safety is 3. This is also assumed. So that the value of sigma what we get, sigma y by FOS, that is equal to 108 Newton per mm square. So once you substitute here, say m is equal to what? M is equal to F max into A. F max into A. So F max into A. F max is what here? F max is 574. So this value is to be used here. 574 multiplied by 725. 574 multiplied by 725. So this value is to be used here. And then H1 by 2. H1 is what? H1 is not given. H1 is not given, so we have to assume that H1 has 3 times B1. So replace this H1 by 3B1, and here also replace this H1 by 3B1. So B1 H1 cube by 12. So that after simplification, we will get the value of B1 as 14 mm and H1 as 14 into 3, that is 42 mm. So these are the two values which are required. So this is what the thing or the design of simple band breaker. So I hope you have followed the steps. So in the next session, I take one more example on the simple band break. So thank you.